Hey, what's up everybody, and welcome back to the Sanctuary. I'm your host, Professor C, and today we'll be talking about anatomy and physiology. Specifically, I'll be talking about our second group of organic molecules, the lipids. So, without any further business, let's jump in. Alright, let's start with some basic terms for lipids, and remember some things from previous lectures to get our heads straight. So remember the term insoluble, meaning that lipids, and again, if we're having trouble remembering, we'll just scroll the word fats up here so we remember that we're talking about fats or oils. We'll distinguish the two in a moment. Are insoluble in water, meaning they don't like the water, they hate the water, right? They're hydrophobic, they're non-polar. All of these things tell us the same thing, just in a different way. They do contain the same thing as a carbohydrate did, carbon, hydrogen, and oxygen, but they're not in a defined ratio, and they can be quite large. You could have dozens and dozens and dozens of carbons, and then even more hydrogens in a single lipid molecule. So fatty acids, or as I'll call them in a little bit, the caterpillars, because they kind of remind me of what a fat caterpillar looks like. Triglycerides, which must have something to do with three, because I see the root tri there. They got three somethings. Turns out they're going to have three tails. Phospholipid, all right, looks like a special kind of lipid that has some sort of phosphate stuck to it. And a steroid, which everyone's heard of before. So let's look at these one by one by one. Start with the fatty acids, or the caterpillars. You can see some of the caterpillars here are nice and long and straight. A few of them start to, get a little kink to them, and then some of them get downright curvy or curly. But to get to the nitty-gritty, a fatty acid is very fancily said here, a carboxylic acid with an aliphatic chain. So a carboxylic acid, or a carboxyl group, you can find it pretty easily if you look for COOH stuck together somewhere. And in most of these worm-like pictures, it's the head of the worm. So if you want to find the carboxylic acid, or the carboxyl portion, I'm just going to go ahead and circle it over and over and over again. Anytime you see this worm head here, keep on circling the worm heads. Those are all the carboxyl groups, the carboxylic acid. The rest of it is what's called the aliphatic chain. And aliphatic just means it's going to form a single tail like that. It's not going to form rings with itself. They could usually have anywhere between 4 and 28 carbons is a good rule on a fatty acid tail. Okay, so why did some of those worms on the previous page, why were they nice and long and straight? And why were some of those worms crooked? Well, let's look more closely at the structure of a fatty acid and talk about the concept of saturation, a saturated fatty acid. First of all, I can find, well, there's my carboxyl group. I know whenever there's a corner, put a C there if there's nothing else there. There's the COOH. There's the carboxyl group. We can kind of list it here. There's another way of seeing it here. And there's another way of seeing it here in our little worm drawing. So there's the head, and then behind it I see a tail, an aliphatic chain. There's no loops to it. In fact, there's not even any kinks to this one. This one's long and straight and rigid. And so here's what you have to imagine in your mind. Carbon has an atomic number of 6. And if we could sketch that out real quick, ignoring the nucleus, because it doesn't matter when we talk about how it bonds, I know it would have 6 protons based on it being atomic number 6, which means it also has 6 electrons. We can distribute those in our energy shells like we looked at in previous lectures. 2 in the first shell. That would leave us 4 more that we have to place in this outer shell. And that puts carbon in a predicament. It's neither electropositive nor electronegative. Right? It doesn't have fewer than 4 or greater than 4. It's got exactly 4 electrons in its valence. And what this allows carbon to do is hook up in a lot of ways with a lot of things, including itself. So when you see a long aliphatic tail like this coming off of our carboxyl group, our worm structure, you have to picture that at every corner there's a carbon, and it's got to make 4 bonds with something to get happy, right? Because it's got 4 electrons already. It's going to make as many as 4 bonds, so we have to keep these all straight. If I know this is the carbon chain, carbon, 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 then this carbon here, say for instance, it is linked to this carbon, and we only see 2 bonds. But I know it needs 4. So what's not shown is the 2 H's that are stuck out like that. This one here would also have 2 H's. And this one here would also have 2 H's. In fact, you can see that really well in this next picture, where they're showing you CH2, 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 CH2. And then if you follow the tail to the very end, you'd have a carbon there. You still need 4 bonds though. So you'd make a CH3, and that's exactly what you see there at the end of the worm is a CH3. Or these bumps in the tail like that, that's a CH2 group. That's a CH2. And that's a CH2 and a CH2 and a CH2 and a CH2, and at the end is a CH3. And that's what you're looking at, the chemical structure of a fatty acid. Now, what makes it saturated? Well, again, this picture shows it very well. At every place where carbon's trying to make 4 bonds, it is linking up with the maximum amount of hydrogens. And so it doesn't need to double bond with itself. Carbon, carbon, carbon is all single bond, single bond, single bond, single bond. So we have all single bonds to the carbon. We have the maximum number of hydrogen atoms, CH2, 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 until the end CH3. This makes it saturated. We say that the molecule is saturated with hydrogen. Now because of this, because it's long and straight and has no double bonding and is just single bond carbons with CH2, 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 at room temperature, it will be solid. All right, so think about some solid fats that you know about, like butter and lard. These things would be considered to be saturated fatty acids. Okay, so what if the worm gets kinky, right? What if the worm is bent? Well, this would be an unsaturated fatty acid. And when we look at the comparison here, we can see, hey, there's our COOH, there's our carboxyl group. There's CH2, 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 and then at the end CH3. Nothing fancy going on here. There's the maximum number of hydrogens bound to that carbon chain. That's a saturated fatty acid, nice and long and straight tail, no kinks. But the one under it, the unsaturated fatty acid, it has lost some hydrogens. So notice here where we formed a double bond, some hydrogens have gone away. They've left, one from one side and one from the other side of that double bond, and carbon still needs to have 4 bonds to satisfy its valence. So in order to do that, it double bonds with its partner. And it has lost some hydrogens, therefore now it's unsaturated. And it also has a kink in its tail, and that's the immediate way to tell the difference between saturated fats that are long and straight and unsaturated fatty acids that have at least one kink in the tail. One is enough to make it unsaturated. The more kinks that it has, the more unsaturated it could be. And you could even hear of something known as polyunsaturated fats. They would have many, many kinks. This is not one, but we do see some over here, especially like these wiggle worms right here that are definitely kinkier than the guys on the other page that were nice and long and straight. So lots of double bonding going on, lots of unsaturation going on, and we have a long, kinky, curly tail. All right, so an unsaturated fatty acid would have at least one, but maybe more, double bonds between the carbons. Makes the tail more flexible, more wigglier, and then at room temperature you would expect this to be a little bit not so solid. So these would be liquids, and we would call these really oils when we think about cooking oils and so forth. This is a good example of unsaturated fatty acids. All right, our next group of lipids are our triglycerides. Now, it kind of sounds like it's 3 glycerides, and it's not actually that. So let's look at it real quick. It's going to be, if we could sketch it out, it's going to be a head of something called glycerol and 3 fatty acid tails. Now in this example you can see that. Here's a glycerol. There's our head. Alright, you can see there's our carboxyl, carboxyl, carboxyl. So it looks like there's 3 fatty acid tails on here. That's a triglyceride. So a glycerol head plus 3 fatty acid tails makes up a triglyceride. Now, if you notice, all 3 of these tails are long and straight. There's the maximum number of hydrogens bound to each carbon in the chain, CH2, CH2, CH2. No double bonds between the carbons, so no kinks in the tail. So you have 3 tails that are all saturated fatty acid tails in this triglyceride. Now, triglycerides can also be called neutral fats, solid fats, liquid oils. There's a lot of different things you can call these. Made up of 3 tails and a glycerol head. And the function of these is to store energy, to add some insulation to your tissues, and some cushion to some of your tissues and some of your cell types. So protection would be a good function for triglycerides as well. Alright, a special case. Remember our triglyceride? We had a glycerol here, and we had 3 tails, but let's change it up. Let's give 1 straight tail and 1 crooked tail, and then the 3rd tail is missing. So we started to draw a triglyceride, but we only got the glycerol head and 2 of the tails. Instead of a 3rd tail, let's stick up here somewhere what's called a PO4 group. And you can see this in this image where I'm making this arrow point. The PO4 group, that's called a phosphate group, a very handy functional group to know. PO4 is a phosphate group. So instead of that 3rd fatty acid tail, we've replaced it with the phosphate head. And when we did this, this gives a interesting property to phospholipids. It makes the head polar and the tails fatty, still the fatty acids nonpolar. So you see that the head likes the water and the tails do not, and it shows it right here a different way. Same information. And that's kind of the little easiest way to write a phospholipid, is just draw a ball with 2 sticks coming out, and you can very quickly sketch out the glycerol head and the 2 tails. So a few different ways of drawing a phospholipid here, and we'll definitely need these modified triglycerides when we start building cell membranes. So interesting chemistry to these. We will definitely be talking about phospholipids, probably more than any other type of lipid in further discussions. Okay, the last group of lipids, the steroids, also known as sterols, have this structure you see up here. Let me kind of illustrate it a little bit better. It says they have a 4-ring structure, and if you're not really familiar with chemistry, it's kind of hard to see at first. Well, here's a ring right here. Again, a hexagon. That's not an aliphatic chain, right? That makes a ring. There's another ring. There's 2. Here's a ring right here, and there's another ring right there. So there are 4 rings, and then the guy hanging off the end kind of looks like a fake ring, but actually it's just a tail hanging off. So this 4-ring structure and then a tail is your classic image of a steroid or a sterol. Now you're probably familiar with a very important sterol known as cholesterol. Now we pronounce it cholesterol like a normal human being, but is an example of a steroid. vitamin D and testosterones and estrogens, the sex hormones, bile salts that work, from the gallbladder to help regulate digestion. So steroids are not bad things. You must have steroids in the body at the right level to function correctly. Just remember, steroids are also called sterols, and cholesterol is usually the prime example on most tests. All right, as usual, thanks for watching the video. If you enjoyed it, check out the other videos in the series, and I'll see you next time. Bye-bye.